Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to take a look at how we can do the Monte Carlo simulation with Gaussian distribution. In the previous video I covered how we can do Monte Carlo simulation in LTSpice. Just to recap or refresh your memories, I'm going to show you in the help of this LTSpice. You can just write MC and hit enter, and you can see this in this table, MC of x and y, which means a random number between x times 1 plus y and x times 1 minus y with uniform distribution. Now we're going to take a look at how we can do with the Gaussian distribution, because as you can see in this picture, most of the times when you have a variable in the circuit, variable could be the dimensions of your transistor W or L, or could be the threshold voltage of the transistor MOSFET, or the value of resistors or capacitors. These kind of things could be changes. So, and the best distribution that we can define for changing these variables is the Gaussian distribution, which you can see 99.7% of the times we're around the mean value or the average value or the nominal value of that element. But as you can see, when we go far away from the mean value, which is here is mu, the probability of getting that values are almost zero, and it decreases somehow. So we had to define this kind of distribution for our Monte Carlo to be more close to the real world. And I'm just going to take this as a simple exam for you guys. This is a 1 kilo ohm resistor with the current of 1 ampere, and we can see the value for Vx first, and then we're going to define the tolerance of this resistor as a Gaussian distribution. We can see how we can do that. Just as the beginning, I'm going to run the simulation. This is a pretty straightforward simulation, and the stop time would be 100 milliseconds. So now we're going to take a look at Vx value. Vx value is 1 kilovolt, because 1 kilo ohm resistor with the 1 ampere current. So 1 kilovolt, the voltage of this node X. Now we're going to run the Monte Carlo simulation. How we can do that? I mentioned that this is from this reference paper, application of LTSpice modeling to Vishay temperature sensors. You can take a look at these as a real reference. This is a really great reference. So now how we can define? We had to define a new function in order to do that. And for this function, just in search, you can, in the help, you can search Gauss for Gaussian distribution. Hit enter, and you can see there. This is how you can define Gaussian distribution. Random number from Gaussian distribution with sigma of x. This value on the parentheses is the value of sigma for Gaussian distribution, not the value of the mean. So how we can define it? This is how you can define it. Then we're going to define a new function, dot func. This is a function. Now you have to write a syntax how you can define it. For example, MCG, Monte Carlo, G for Gaussian distribution. Now we need two numbers, x and y. X for the value, the nominal value, y for the tolerance of that value. Okay, now we define our function between two closed oculots. We're going to use if. How we can use it again? And it's here. If with three statements, with three options, x, y, z. Let me close a little bit. If x is greater than 0.5, then y, else z. Now I'm going to put some numbers into this. If, let me just write it first, x equals equal to 1, the value is x, and otherwise the value would be x times 1 plus Gaussian value of the sigma. Sigma could be the tolerance that we define into our resistor element. Okay, let me just make this font a little bit bigger so that you can see it. Oh, it's just too much. Maybe 2.5 will do the job. Yes, of course. So as you can see, this is a function. If x equals to 1, I think I made a mistake. X is the value for I want to put x as the value for this resistor in here. You see, I'm going to define this as something like that. MCG is the name of the function. Two values, 1 kilo ohm for the nominal value, and for example 0.1 for the tolerance of this resistor in here. So x is the nominal value of resistor. This shouldn't be x. This should actually be run, because now we had to define dot step function for parameter run from 0 to, for example, 100 with a step of 1, and maybe a little bit bigger than this, because we require more than one simulation for Monte Carlo. So here, this is, let me just run this simulation. Maybe we had some problems, I don't know. Yes, dot step, syntax error for dot step. You see, if you face with these mistakes, don't worry about it. Just go to the search and type step. Now you will find dot step. What is the syntax? So here, this is the syntax. Dot step. Oh, okay. Dot step. After dot step, you had to define how this variables is going to change. So it's in octave, it's linear, param. What is it? Now this is a parameter. Dot step. So after that step, I'm gonna write param and then run from 0. Run from, no, not 0, from 1 to 100 with a step of 1. And if run is equal to 1, this is the value for resistor, which is 1 kilo ohm. Otherwise, this is going to be the Gaussian distribution with the sigma of 0.1. Okay. Now I'm gonna hit the run. So can't find definition model of MCG. Okay. Now maybe we made a mistake again. Let me just check that. This is really important for you to overcome these issues. This is going to help you and learn you a great deal, finding your errors. Maybe there is something with the syntax. So here we have, what do we have in here? You can hit a space to fit in your whole LTSpice page. So here, this is MCG X and Y. So here, MCG 1 kilo and 0.1. What is my mistake? Oh, this is my mistake. Here I define it as X and Y. Here I place X, but here I write tool. I had to write Y in here. Y tool, Y. Okay. That's my mistake. That was my mistake. So now I'm gonna hit the simulation again. Select OK to continue. So still we have problems. We have problems in here. Unbalanced. Okay. Error unbalanced parentheses. Okay. Now it's easy to resolve this. Now one parenthesis for y, the other for this one, and how about this if one? Okay, we need another parenthesis to close and define this function very well. Now that's it. Run the simulation, and as you can see, this is all the different values for Vx, which is, as you can see, around the 1 kilovolt. There are lots of values around this. This is a Gaussian distribution, but other than this, as you can see, the values are rare. This is how you can define a Gaussian distribution for your Monte Carlo. And as I already told you, this is the reference for this video. This is a really great paper. You can watch it and learn a great deal other than this from it. Okay guys, that's it for today's video. I hope you learned a lot, and remember that you learn a great deal from making mistake. Okay, this is really important. If I walk you through this, for example, even in the simplest functions and syntax in here, this is really important for you to do it yourself. Okay, you learn a great deal finding your errors. This is really important. This is why I try to walk you through this, and simultaneously you can see with me what are some errors, how I can actually address those errors. Okay, this is really important for you to learn a lot. Okay guys, I will see you in the next video. Thanks for watching.